Next up, we have Mingshuai, and he will talk about lower bounds for possibly divergent probabilistic programs.
All right. Thanks for the introduction. Hello, everyone. My name is Mingshuai Chen. I'm an assistant professor from Zhejiang University in China. I'm going to talk about lower bounds for probabilistic programs. In fact, a new proof rule, so I'm kind of like to challenge Philip for his tool to encode the new rule. This is a joint work with Shenghua, Feng, Han-Su, and Naijun, Zhan from Chinese Academy of Sciences, as well as Benjamin Kaminski from Saarland University and Joost-Pieter Katoen from RWTH Aachen. Before I go into the very technical part, let me start with some fun fact, saying that a drunk man will find his way home, however, a drunk bird may get lost forever. I think this is a very nice interpretation of the mathematical principle, saying that a two-dimensional symmetric random walk on a lattice returns to the origin almost surely, which is, however, not the case for a 3D dimensional random walk. In fact, the precise probability that a drunk bird can return home is rather involved to compute. And hence, it is natural to ask the question, can we give some sound approximations of quantities like the like the probability of returning home? And in our paper, we provide such a mechanism to answer questions about such quantities from the perspective of computer science. And there, we model random walks as or stochastic processes as probabilistic programs, and the behavior of returning the origin as termination by violating some loop guards. So what is a probabilistic program? You have already seen many in previous talks. So this is a biased random walk where at each step you simply flip a biased coin, and then with probability 1/3 you go to the left, with probability 2/3 you go to the right. This process continues until you hit some termination flag at the origin 0. This is a simple looking program, but it already induces some complex behaviors. For example, because of the biased nature of this coin, this program does not terminate almost surely. All right? And this brings extra difficulties in analyzing such probabilistic programs. And all the difficulties actually come from the fact that a probabilistic program is no longer a state transformer, rather it transforms a state distribution into another state distribution. In order to reason about such programs, we use the tool called weakest pre-expectations, which is a quantitative extension of Dijkstra's weakest precondition. Suppose we start from some initial state sigma here, we run the program C, and we may diverge here with some probability, and we may terminate at some final states. Suppose we are interested in some quantity, let's say f. Here is a mapping from state to some non-negative real number, and then we can simply take the expected value of all those quantities, and this gives us the weakest pre-expectation of the program. We use this WP to characterize the semantics of the loop, of the program C. And in this case, if we take 1 as the post expectation, then this gives us the termination probability of the program C. Let's look at a few examples. Now, the WP of this single assignment with respect to variable n is 5. This basically tells you the value of n after termination of the program will be 5, regardless of the initial state. This is a constant function that maps any possible initial state to the number 5. Here's another example where we have a probabilistic choice. And if you calculate the WP, this gives you the n plus 1/3. This expression tells you that the initial value of n after termination of this program will be increased by 1/3 in expectation. In fact, the WP of all the loop-free fragments from an imperative programming language can be calculated purely syntactically. But there's one exception. So for the loop construct, for example, let's say we are interested in post expectation 1. Basically, we want to ask what is the termination probability of this while loop. And this is not so intuitive anymore. For this particular example, I can show you that this is the precise WP, but calculating the precise WP for while loop is in general intractable. This is because the semantics of the loop, or the WP, corresponds to some least fixed point of some monotonic operator phi. This phi is often called the characteristic function of a while loop. I wouldn't go into detail there, but I hope most of you agree with me that computing the exact least fixed point is in general intractable. And that's why we want approximations of the least fixed point or the semantics of the loop by either putting an lower bound or an upper bound. Now for upper bound, this is easy because we have this very elegant theorem called Puck's lemma, saying that if we push a candidate upper bound u through the characteristic function, and this takes us down in the partial order, then this already suffices to show that u upper bounds the least fixed point. In terms of a picture, we start with a candidate upper bound u. We apply phi, this takes us down in the partial order. We keep doing so until we reach some fixed point. And then by the Knaus-Tarski theorem, this is necessarily an upper bound of the least fixed point. Now, can we have something similar for lower bounds? Namely, by simply flipping the direction of the inequality sign, and we obtain something for lower bounds. However, this turns out to be unsound. In terms of a picture, again, we start from some candidate lower bound L. We apply phi. This takes us upper in the partial order, and until we reach some fixed point of phi. But this fixed point of phi is necessarily a lower bound of the greatest fixed point, not necessarily for the lower bound, for the least fixed point. And that's why we don't have a relation claiming that L lower bounds the least fixed point. And in order to fix this problem, there's a very nice paper by Marcel Hack et al. They propose to use some side condition to fix the problem. And here the side condition basically says the candidate lower bound is uniformly integrable in some sense. And this concept of uniform integrability comes from stochastic processes, which I wouldn't want to go into detail here. But just to give you a bit of flavor, this often requires some extra requirements on the programs. For example, this is only applicable to programs which terminate almost surely, and with some boundedness condition on the expectations. And what we want to do is to avoid such extra restrictions on our problem. To do so, we propose a new proof rule for lower bounds called the guard strengthening rule, and this rule works in a quite straightforward way. For example, given a while loop with loop guard phi and loop body c, we simply rewrite this loop into a new one which differs from the old one only in loop guard. So we have a new loop guard phi prime. Now our rule says if the new loop guard strengthens the original one or implies, then a lower bound for the modified program with respect to some modified post expectation suffices as a lower bound for the original loop semantics. What is the intuition behind that? Let's recall our biased random walk example. Suppose now we are interested in verifying some lower bound on the termination probability of this random walk. We can simply rewrite this loop into a new one by putting an upper bound m onto the variable n here. And m can be an arbitrary fixed natural number. This amounts to putting a barrier on the way of the random walk. And now it's obvious that the new loop terminates either by hitting the left bound 0 or by hitting the right bound m. Now our rule claims that the probability that our new loop terminates by hitting the left bound 0 is a lower bound of the termination probability of the original loop. Why this is the case? Suppose we start from some location n. We can go either all the way to the left until we terminate. This is a valid terminating run for both of the two loops. We can do similarly by taking this, first go right and then all the way to the left. This is also a valid terminating run for the original loop. However, if we somehow want to cross the barrier and eventually terminate, this is a valid run for the original loop. However, because of the barrier we put there, this is no longer possible for the new loop. In that sense, we lose some probability of termination. And that makes this quantity a lower bound of the original loop semantics. Okay, and now, even though in this form the rule looks quite simple, but sorry, I forgot something. That the whole purpose that we do this guard strengthening is in the hope that the modified loop will feature a stronger termination probability. For example, in this case, the loop becomes asked. Okay, and in the hope that it's easier to verify uniform integrability and boundedness conditions on expectations. The rule is simple, but the proof is quite involved, I would say. So we basically investigate the difference between weakest pre-expectations of two arbitrary given loops, where we have to explore different categories of infinite traces. But for the sake of time, I wouldn't go into detail here. Yeah, now let me show you a few nice properties of our proof rule. The first, it is complete in the sense that whenever there exists a lower bound for the original loop, we can always find a strengthening such that this lower bound also lower bounds the modified loop semantics. This is true because you can simply take phi prime equals to phi. Right? But this does not necessarily give you a helpful strengthening because it doesn't do anything basically to the loop. And the second property is that the rule is general, as we have already seen, that is applicable to some possibly divergent probabilistic loop and unbounded expectations. To be more specific, recall our example of the biased random walk. In case now we want to verify something, some ugly-looking expression as a lower bound of the termination probability. And then we can simply apply our rule, and then we reduce the problem to finding to verifying some lower bounds for the almost surely terminating program. And in this case, we can apply existing rules, for example, Hark's rule, to establish such a lower bound. The next property is that our rule is tight, in the sense that you can always pull this barrier up to the infinity, and this gives you the tightest most lower bounds, or under approximations. In our case, this corresponds to taking the limit over m, and this gives you a nice expression independent of m. And in this special case, you can even apply Park lemma to show that this expression suffices also as an upper bound, and hence we can claim that this is the precise semantics for the while loop. The very last property I'd like to show is that our rule can be partially automated, because whenever we can find a strengthened loop which has a finite state space, we can always use probabilistic model checking to find some non-trivial lower bounds for the modified loop. This applies already to our three-dimensional random walk example, where we know that the precise probability of returning to the origin from any neighboring location is something around 0.34. But we don't want to calculate this horribly looking expression. Instead, we apply our rule, and we restrict the state space of the random walk, and then we use Prism, for example, as the underlying probabilistic model checker. Then it gives us a picture like this. So this line indicates the precise probability, and as you can see, when our strengthening goes weaker and weaker to the right, we have tighter and tighter under approximations. This also confirms with our intuition that the further you deviate from the origin, so the further you go down, the lower probability you will return back. The very last example is called zero-conf protocol. This is just used to give you a bit of flavor how our rule can be applied in a somewhat real application. So this is a local network where whenever there's a new device coming in, the network itself tries to assign an unused IP address to the new device. And this algorithm is a randomized protocol because it uses communicating packets in between, and the packets can get lost with some probability. At the end, we are interested to verify some property saying that the probability of the protocol successfully terminating with an established IP address is at least of this quantity. However, using existing techniques, we were not able to do so. For example, the maximum number of packets allowed to send in this protocol is not bounded from above, and hence we cannot use probabilistic model checking. However, by applying our rule, let's say we simply put an upper bound 10 here, and then we were able to use some invariant synthesizers to find a good enough invariant to certify such a lower bound. In summary, we have presented a new lower bound rule based on WP difference and Gauss strengthening. This rule, to the best of our knowledge, is the first one that admits divergent loops with unbounded expectations. And our rule often produces tight lower bounds, for example, for the three-dimensional random walk and the zero-conf protocol. There are much more in the paper, for example, how to find a good strengthening, how to generate a non-trivial lower bound for the modified loop, and some corner cases where the Gauss strengthening is insufficient. If you are interested in that, check out our paper. With that, I'd like to conclude my talk, and thank you very much.
I think we have time for maybe one question. Okay, I'll ask a question. It was nice to see one practical application of this. I was also kind of curious, are there examples where this guard strengthening doesn't work? And could you maybe say a little bit about what kinds of programs those would be?
Yes, short answer is there is. I have two examples of this. So I wouldn't go into detail of that, but basically the first example says there is a program where just applying a very trivial strengthening does not work. Let's say simply putting a bound on some variable. This does not work. But we carefully tune such an example such that the variable takes values in a spiral pattern such that you can only use a circle as a strengthening, right? And the second example says there just does not exist any meaningful strengthening. We also have an example of that. Yeah.
Got it. Thanks. Let's thank the speaker one more time.